Yeah, thanks a lot. It's very nice to be here, everyone. Let's keep this real casual and feel free to jump in with clarifications or questions. And I'm very happy to chat about this more afterwards as well. And if I don't get enough questions or comments from you guys, I might start asking you some questions. So you've been warned. But like Don was saying, this project was kind of birthed because myself, a postdoc I work with, Josiah, and my advisor, and also Misha Lukin and some of his students, about a year ago, we really started to think about what is the most impactful thing we could do with Rydberg arrays. And obviously it would be to build an error-corrected digital quantum computer. And we started to think, what are the roadblocks going to be in the future to really pulling that off? And how do we avoid some of the pitfalls that some other hardware platforms have run into as they've attempted to scale and really turn this into something impactful? So we started thinking about that more in a Rydberg context initially. And then eventually some of the results and ideas that we generated, we realized were a little bit more general. So we ended up writing a paper just based on that, which is more of a kind of pure error correction surface code paper. So please do check that out. There's a lot more math in there than I'll cover in the talk today. And then we also are in the process of writing up a follow-up kind of illustrating how we'd take these concepts and implement them on Rydberg arrays, and how Rydberg arrays are probably uniquely suited to realize this kind of stuff, but also it could generally apply to other platforms as well. So I'm interested in talking with people from superconductors and ions, and also thinking about how we could map into those kinds of systems too. So this is the outline we'll cover today. First, my co-authors and I strongly believe that the idea of modularity is very, very important to actually scale and satisfy what we would consider the definition of scalability. So we'll kind of talk about that. We'll go through kind of how to think about that and how that's created problems for scaling and in other platforms, and how we're thinking about dealing that with Rydbergs. Then we'll go through and talk about some theory stuff about what exactly the fault-tolerant requirements would be when you want to interface different kinds of modules, and how that's probably the most challenging part of actually building a large-scale quantum computer. And because in quantum error correcting codes, we're all about thinking about robustness to noise, that's really going to be the bottleneck, we think, for building a large-scale quantum computer. So it merits quite a bit of thought and analysis. And we'll go over some of the ideas we've developed in that direction. And after that, I know that I've gotten a lot of interest from people here in understanding the Rydberg arrays a little bit more specifically. So I'll give you guys an overview of kind of where they are right now, where they're projected to go, and then also how we think we can fit them into the framework we developed for the modular architectures. So let's talk about why modularity is critical for scaling, first of all. So if you think of a given hardware platform or technique for quantum computing, you generally see that there's some kind of a trade-off curve like this. So I like to think about putting the mean gate fidelity, say your 2-qubit gate fidelity, on your y-axis, and then think about increasing or stuffing more and more qubits into your system on the x-axis here. And there's generally some kind of a trade-off where the more qubits you stuff in, the harder it is to keep everything under control and maintain that same gate quality while you're trying to control more and more qubits at the same time. So you end up with something like this orange curve here. And of course, exactly what that looked like depends on the hardware you're talking about, how much engineering work you've put into it, and whatnot. But over the last couple of decades, we've seen a variety of hardware architectures try to push this orange curve further and further to the right, to try to scale up, adding more qubits to Dill fridges, stuffing more ions into chains, right, putting more Rydberg atoms in an array, stuff like that, trying to move this orange curve to the right. And that's a great thing to do and very important. But the problem is every time you want to, say, double the size of your system, you want to move that orange curve to the right, you usually have to solve brand new engineering challenges. You always run into something. There's a lot of issues, and we'll go over that in a few examples in a minute. So the modular approach kind of cuts this short. And what it does is it gives you a definite task. And once you accomplish it, you actually are scalable in the sense of you just need to pump out more and more modules and then connect them all up together. And at that point, you can just scale in a way that's just linear with the amount of money that you're willing to put into the system, rather than at each additional size scale having to solve brand new engineering challenges, some of which are potentially impossible to improve on at some point. So if you do adopt a modular design, you have the difficult task of actually getting the modules to interface with each other. But once you've actually accomplished that, then you're done, right? And it reduces to just having to run an error correcting code, if you want to do it fault tolerantly, across multiple modules. Okay, so let's just go through a couple examples that I think are good to keep in your mind about the trouble that's run into by various platforms when they attempt to stuff more and more qubits into the same unit. And you'll notice if you actually go to many of the different companies' websites that offer roadmaps, and you can't take these too seriously, right? But it's kind of like some hand waving at the future, and you can get their take on it. They all kind of admit that at some point they run into some kind of size scale issue, and they're going to eventually connect everything up with links, right? So you can look at IonQ, you can look at their roadmap, right? Obviously, they're saying they're going to have way more qubits all connected together in the future, right? And if you read the article that they post along with their roadmap, they say some point in here, we're going to have some links between ion chains, right? Same thing with IBM, right? Same thing with Google. Their roadmaps, they all have some point at which they realize there's going to be some technical issue, which is pretty much going to prevent controlling more qubits in the same unit, and they're going to have to expand beyond that via some kind of networking, which is not really figured out yet. Let's just go over a few of the actual challenges that they run into. For example, the ions. Well, they try to add more and more per chain, but eventually they run into spectral crowding of the motional modes. They use these motional modes to communicate between ions. When you stuff more in, you increase the mass of that chain, and then eventually you can't actually communicate well because the motional modes get crowded. With the superconductors, we have cryostat size and power and cooling power issues, and also chip fabrication is very difficult, right? There's a certain post selection that you need to do when you fabricate the chips because of defects. It's harder to make those bigger and bigger and bigger. And then more in my wheelhouse with the Rydbergs, right? The Rydbergs are a little bit more of a dark horse, and so they don't have a company with like a whole roadmap kind of worked out yet to even screenshot and put in this presentation. But eventually, we're not going to be able to put more in either. We have some microscope objective. We have a whole bunch of lasers. We're trapping all these atoms in there, and eventually, we're not going to be able to fit more than probably around 10,000 in an array because the microscope just can't see more than that. Is one issue. There's also other technical issues as well, laser power things, other control issues, which will make it difficult to get beyond that. So we think we can get pretty big, but again, not really big enough. So if you look at all these examples here, they're well on their way to be able to support like local error correction. They might be able to get a few qubits locally, logical qubits, right? Functioning well below threshold. And that would be an amazing scientific achievement, right? But it's still not really what we're looking for, right? We want to be able to connect lots and lots of these qubits together in a way that ultimately scales linearly with money if possible. So all these companies admit that at some point that's going to require some kind of links, right? And the thing about links is that they're likely to be the noisiest part of the whole program, right? It's actually much harder to take quantum information out of a unit successfully, move it to a different unit and put it into that unit. There's a lot of moving parts involved. There's a lot of different kinds of components. There's just a lot of parts to take care of. And it's much harder than just having two qubits sitting next to each other and doing your native, 2 qubit gate operation. So that's where the noise is likely to be the most stringent. And so it's really important to understand how your error correcting code deals with that noise and try to work the hardest we possibly can on the theory to relax that as much as possible for our hardware compatriots. So let's try to understand this bottleneck to fault tolerant scaling, and in at least to start with in the context of the surface code, which is something akin to that is what all these platforms are shooting for because of its obvious advantages, which I think we're all familiar with. So let's talk about fault tolerance requirements when you're interfacing modules, specifically modules made out of surface code patches. So the way we're going to think about it for the context of this talk is that you might have a error corrected qubit, say on the left half of what we call the seam here. That would be a logical qubit in some module. Then you have another logical qubit on the right here, to the right of the seam in another module. And you could use, say, lattice surgery or just move the qubit between modules or do something like braiding. Those all reduce to supporting check operators which just cross the seam. So you can imagine just take a big surface code patch, kind of draw a line down the middle and stretch it out. And you realize that there's this region here, the seam, and you need to have one leaf of each check operator span between modules. So that's a good mental model to use to think about a way to get these modules connected up. And it's nice because it just reduces down to running a common surface code across both modules at the same time. So the thing to note about this, and as far as I know, Austin Fowler was the first to mention it, him and Rodney Van Meter and everybody. They had a paper around 2009 where they noted that when you have asymptotically small bulk errors, and we'll call the region within each of these error corrected qubits the bulk, as opposed to the seam, where we're going to have elevated levels of errors. When you have asymptotically small bulk errors, okay, this seam here reduces to a repetition code. and it's lower dimensional than what's going on. And that can lead to you being able to tolerate more noise along that lower dimensional boundary. And we'll talk about that more in a minute. But to bring this concretely to the idea of links and to think about when you do these long range gates, how the noise propagates, you can actually just insert the typical circuit for a teleported C0 gate, which looks like this, where you have a bell pair in the middle. And then, you have this qubit and this qubit are that one and that one across the seam in the two modules. And then when you introduce Z and X errors on the bell pair here, those propagate through the circuit, and they actually land to the right and to the left of the seam. And so to take a concrete model for the rest of this talk, you can actually propagate through the circuit and realize that X errors end up to the right of the seam, and all the Z errors end up to the left of the seam. So then if you break this down and use an independent X and Z decoder for simplicity, you can imagine that it really is just a one-dimensional problem here when it comes to the X decoder, and then a one-dimensional problem here when it comes to the Z decoder, again, in the asymptotically small bulk limit. Now, of course, when we have noisy syndromes, we know that we have to repeat the error correction many times. And so instead of a 2D matching graph, when we decode, we actually have a 3D matching graph. What that means is if you look at what's happening along the seam, the bell pair noise gets deposited both on the data qubits and on the syndrome qubits. So when you actually kind of extrude this into the third dimension and think about your 3D matching graph you're going to be decoding over, it's actually the pink edges here that are the ones that have the elevated level of noise. So again, this is the 3D matching graph. We have a space dimension and a space dimension. So that corresponds to, say, the two space dimensions right here. And then this seam right here, right? If I extrude that in time, I have pink edges not only in this space dimension, but also in this time dimension, because both my data qubits and my syndrome qubits are having this extra noise from those bell pairs deposited onto them. So it turns out that the case of interest that we want to explore is what happens when we have elevated noise on a 2D sublattice within this overall 3D lattice, right? So we'll have a decoding problem. We'll have a lot of noise, extra noise on these pink edges. We'll have a smaller level of noise because we have higher quality local operations over here on the black edges. And then we want to know, what does that mean about the properties of the noise robustness overall when we have the combination of these two. So again, 2D sublattice within 3D bulk. This works for something like lattice surgery, extending qubits. You end up with a 1+1 dimensional subspace. So question for you guys, though, since I haven't had any comments yet. What would happen, let's say, if you want to do like a transversal gate instead? So instead of using this paradigm, I have two separate code patches, right? Instead of per code cycle, kind of distributing something around the order of L bell pairs and then kind of stitching them together like this. Let's say I had two different code patches. I distributed order of L squared bell pairs between them, right? Noisy. And then I just, in a single round of error correction, I just did all L squared bell pairs together. Would things look like this, or would things look different? Where should the pink edges go? Do you guys have any ideas? I think you can get this. Anybody? So if I do a transversal C0 gate, right? I can take a whole surface code patch, and I can take a whole nother surface code patch, and I can just, in my mind, bring them together. And then I can do local C0s across all the data qubits, right? From every data qubit in this code patch, it functions as the control. And then over here, this is the target. And I just transversely do all the C0s, right? But this happens in a single code cycle, right? So it happens in one time step, right? So you can imagine you're doing a whole bunch of just memory error correction. You're just keeping your qubit all nice and steady. And then you do this, transversal gate, right? And that dumps a whole bunch of noise in at a particular time, right? But it dumps it in across all of the data qubits at that time, right? And so I wouldn't have something that looks like this. Doesn't need to extend in time anymore, right? So I don't need pink edges which go up in time. But I'm actually kind of messing up all of the data qubits in space, in both space dimensions now, instead of just on the boundary right here, okay? So since nobody got it, I'll show you guys. It actually looks like this, okay? So you should imagine that instead, when you do the transversal gate, all of the pink edges are now in two space dimensions instead of a space and a time dimension, right? Again, the idea is I've been doing error correction locally on two different surface code patches. I do a transversal gate between them using noisy teleported gates in a single time slice, right? And that introduces noise on all of the data qubits in that time slice, right? But then I follow that up with more rounds of really high quality local error correction, right? And so everything is black above and below that.
But is it not still like the repetition code down?
That's exactly right. So the point is, it's still a 2D sublattice within a 3D bulk, okay? So all the results that we're about to derive over here, they apply equally well if you're doing noisy transversal gates between surface code patches in two different modules. So I just want to illustrate this because there's kind of two main ways people think about doing gates between patches, transversal and something more like lattice surgery. But in both cases, you can see that the pink is a 2D subspace within a 3D decoding graph. And so all the results are identical. So everything we're about to say applies no matter the paradigm that you choose to work in. Yeah. So I'm imagining in this case that you're actually mediating it by, say, order of L squared bell pairs that you've distributed. Okay, so I have a surface code patch in like the right module and the left module. I distribute order of L squared bell pairs between them, and then I use those to do the transversal CNOT. Does that make sense? Yeah, thanks. Okay, so if let's go back for 1 second. So if I could not have to decode over this whole thing together with the pink and the black edges, and I can just isolate it to one at a time. So I can think about either I have this decoding problem over the black bulk or over the pink seam. You'd actually end up with two separate decoding problems, and they each have different thresholds. So if you want to do the decoding over the bulk, right, this is just a noisy surface code, you get something like a 1% threshold, and you can numerically calculate the estimates of that for under some noise model or whatever, you get about 1%. Now, if you do it for the seam alone, right, so that's just a 2D surface code. And so that has a threshold of about 10% in a phenomenological model. And that's the right model because we only have like one bell pair introducing noise per edge in that. So 10% really is the right number. Whereas this 0.75%, that kind of has to take into account the fact that you have check operators, which have multiple CNOTs within them. And then also the fact that you're in higher dimensions and you can have error chains all over the place and stuff like that. But if you really thought about the decoding problem separately, so there was no interaction, so to speak, between errors which occur on this 2D subspace and then the 3D bulk, you'd really have just two separate problems like this. And you could think of a separate threshold for the seam at 10%, and then separate from a threshold for the bulk at about 1%. And then you'd really just have to design your hardware to satisfy each of those. You'd want your bell pairs to be less than 10%, and you'd want your local gates to be less than 1%, and it would be game over. But that's really not the case at all. All right. So if, again, Austin's work kind of explained everything I've said up to now, which is that if you have asymptotically small errors in that bulk, yeah, you really do only have to worry about your noise along the seam, right? But that's not going to be the case. And we want to understand how these errors actually interact and what that means for threshold and sub-threshold behavior of the code overall. So let's just work through a quick example here. So I'm going to say PB equals 0. What I mean by that is that there's no errors in the bulk. We only have errors along the seam. So here's an example of some errors that I've dropped in along the seam, right, due to this extra bell pair noise on the interface between these qubits. So I have 3 bit flips here, right? Well, if I run my minimum weight perfect matching decoder on this, I can decode it, right? Because along this, say, one-dimensional subspace, I just have, 3 X's and 4 open spots. And so I can just count those up and say, yep, I need to flip these back, and I'm able to successfully recover. Right? But if I turn on noise in the bulk, I take PB from 0 and I make it non-zero. Now I start to drop errors all over the place in the bulk as well. And if I drop some errors here, for example, now, even with that same set of seam errors, I will fail instead of be able to recover, because minimum weight perfect matching will now jump out into the bulk, go through a bunch of these errors in the bulk, jump back onto the seam, and then make its way to the end. And this, is a non-trivial loop and a logical failure when it comes to the surface code logical space. So I was thinking about that during her talk too, and I need to review the XZZX surface code paper again. But I believe that what you simulate in the XZZX code when you talk about like the low dimensional subspaces is actually kind of a special case of what we're about to consider. So it's kind of as if you have planes, right, separated by one edge. Yeah. It's like a whole bunch of 1D codes all stacked up against each other. That's right. And so what you're then doing is you have like a seam and a seam, and then you're hopping, but it's basically all seams except for the edges connecting them, right? Yeah. So the formalism we're about to develop makes the most sense where you have one seam and then a bulk surrounding it, but I'll actually talk about how to kind of put everything under one hood when we come to the end. And yeah, need to review the XCZX paper again to say confidently, but that's my intuition at this point. Yeah. Okay, so we call these hops off of the seam and then back on excursions. And these excursions, how deep they can go into the bulk depends on how far the bulk itself is below the bulk's threshold, all right? So if you have very low errors in the bulk, or let's say, first of all, you had 0 errors in the bulk, then you could only have, but you had like the seam errors were something like near the 10% threshold, then you could only create logical errors by running along the seam itself, right? And if you make the bulk very far below threshold, say 10 times below threshold right here, right? And you simulate what happens and you look for what the shape of the error chains look like, you'll see that it's only very rare that it's going to jump off of the seam, right? And that's because the bulk itself is very, very high quality, right? And it's costly to add errors that are not on the seam. And so you're just going to see very small excursions. It's going to hop off, but then it's going to hop on very quickly. It's too expensive to go way over into the bulk. But as you start to crank up the bulk errors, you're going to see more excursions, and they're going to go further and deeper into the bulk. And so here's an example of like 50% below threshold. Here's 2 excursions. We hop off and back on. Here we hop off a little bit deeper and then back on. And then when you start to make the bulk much closer to threshold, you start to see like crazy long excursions going way into the bulk and then back on. This one's even going backwards, So don't take these as statistical statements because I've strongly post-selected them to like look pretty for the presentation, but this is the general trend that you see as you look at what the error chains that end up failing for different levels of bulk error look like. Okay, so how do these excursions affect the threshold and then also the sub-threshold behavior of the surface code? So we're actually going to go back and review some work done by Dennis and Kataev and Preskill in their famous topological surface code paper. And they were able to prove bounds on the threshold of decoding the surface code in various dimensions. And not only are those results kind of cool to prove that the surface code does indeed have this threshold, but they're also kind of instructive when you think about the nature of the failure for what they treated, which was the case of homogeneous noise across the whole surface code. And it really comes down to a competition between the number of possible failure modes, if you count those up, and then the probability to generate a particular failure mode, all right? So the intuition is that as you grow the size of the surface code, there's kind of an exponentially increasing number of ways in which you could imagine picking the failure mode, right? But there's also kind of an exponentially decreasing probability of a particular failure mode being generated on a round of error correction, right? And then just to give you a heuristic, you can think of this term here, which is the probability. It's kind of like a p to the L over 2, because with minimum weight perfect match, you only need to fill in about half of them. And then there's kind of a degeneracy factor out front, a 2 to the L, because there's kind of like a n choose k effect of like you can pick whichever ones you like to be the half that have failed of the path. So you kind of multiply the number of possible paths, kind of like an entropy factor, by the probability per path, and you can generate a bound or come up with a bound on this. A way to bound and express the number of non-trivial paths is actually the number of self-avoiding walks that you can have on the lattice. And you understand this, you start to understand the impact of dimensionality on the threshold. Because if you're sitting somewhere on a lattice and you want to extend your error chain, you've already just walked a certain distance, but then each dimension that you have available, you can go either direction on. And so you get a factor of 2d minus 1 to the L, where L is the number of steps that you want to take. So again, each time you want to take a step, you have d dimensions in which to move. You can move either left or right on each dimension, so that's 2d, but you can't like go back on yourself where you just came from. So that's why each time you move on the lattice, you have kind of like 2d minus 1 choices. So then if you want to bound the number of possible paths that you could have, well, if you're of length L, then you'd have 2d minus 1 to the L, because each time you have that number of choices. So this is not a tight bound, but it's a way to get a handle on the intuition behind how the number of how the growth of the number of non-trivial paths depends on the dimension. So you can kind of just put these two together, and you can come up with something like this, where you have kind of like a prefactor, which is dimensionality dependent, times the probability per link, and again, in this homogeneous noise level, and you raise that to the size of the system. And then that's what allows you to actually generate a threshold bound. So stars will indicate thresholds in this talk. How am I doing time-wise, just to kind of check? Okay. Now, what we found useful kind of at the end when we wanted to look back and understand where we went with this project was that you can gain some intuition, again, by really taking seriously what happens when you're trying to extend an error chain. So you can imagine there's an error chain. It's not extended across the whole lattice yet. It's kind of like a few links long. And then, it's trying to decide whether it's going to grow longer or not, right? And again, there's a competition between two effects. There's kind of, you can kind of rewrite our expression before as just something to the L, where L is kind of like the rough length of the error chain and how far it has to propagate in order to generate a failure mode. And you can think about it, it's competition again between the number of ways that it could append another edge, and then a probability factor that actual edge is generated during the error correction. And again, it's a square root because of the way that minimum weight perfect matching occurs. You only need every other one. So it's kind of like that, and you have a degeneracy factor. So you can think of this as a rough kind of like probability to generate the next edge. And then this is kind of like a number of ways in which you could go. And so the number of chances you have to generate that next edge. And it's a competition between these two. And then the threshold condition is when this thing is equal to 1. But that's just reviewing it for the case Dennis treated, because it's about to be a powerful conceptual way to generalize to more complicated scenarios. So see our paper for an actual rigorous kind of like analysis where we go through and we actually add all the possible ways you could have excursions of all possible lengths and kind of like treat everything and manipulate a whole bunch of sums to come up with this result that's up here. But to kind of skip to the end and just get the intuition for what happens, when you turn on the bulk, you end up with effectively more ways in which to add links on the seam. So whereas before we have just mu s, which is the number of ways if I was on the seam to stay on the seam and say move along while staying on the seam, what you should add to that is another giant term, which captures all the ways in which you could append another seam link by first jumping off into the bulk, running around for a while, coming back, and then hopping onto the bulk, right? And this makes a lot of things make sense in terms of our results, because if this thing, if PB was 0, the bulk was 0, right? It would reduce to just the mu s here, and we have the usual seam threshold. If you turn this thing on, right, it effectively makes the number of ways you can add seam links larger, which slightly reduces your threshold, right? Because then that PS here now has to be smaller in order for this whole thing to equal 1 when this is now non-zero, okay? So we can take that whole thing, kind of factor out the root PS, and the original seam threshold PS star. And then we have something like this, where we have 1 plus a factor here, which depends on how far below threshold the bulk is, or the actual value of the bulk here. This alpha C is kind of a counting term, which in the bound case is like the number of ways it's possible to leave and return to the seam. This term itself kind of has two parts to it you can think of. The first part here you can think of as the probability to actually spawn a particular excursion. You kind of need to stick out with two edges at the beginning and end of the excursion, and those are bulk links, and so you have to pay the bulk probability price in order to actually have that occur. And then once you're out there, you can have an excursion that's as long as you like. So you need to sum over the possibility to go, with a short excursion and a long excursion and all the way out. And you can like resum that, just a geometric sum, in order to get this expression and actually bound what happens. But then you can actually take this whole chunk right here and just move it down into PS star. And you can see that this is effectively making PS star kind of sag a little bit. It used to be at that nice 10%, but then when you have the bulk, you have all these extra ways to kind of like leave and come back to the seam. And so PS star moves down slightly, and we can rigorously bound how much it moves down. But the result is that, yes, we can actually prove that you can relax the bound on this subspace in exchange for a slight sag in the overall performance of the code. And the question is, how slight is that, right? And so to kind of express this, we're going to say that we're going to first fix the ratio between seam and bulk errors, so that the ratio between them is just the same as the ratio of their nominal thresholds. And then we can plot our results for the analytical bounds. And again, you see that there's a certain threshold you have when you have them totally independent. And then when you allow them to interact together, that threshold sags a little bit. The other thing to note, though, is that as you go far below threshold, like not too far, even just a few times below threshold, you see that there's a convergence of the logical failure rate to what happens in the absence of interaction between seam and bulk. And again, the intuition for that is that as we make the errors smaller and smaller and smaller in the bulk, it freezes out the ability to do any excursions whatsoever. And so when you're, several times below threshold, again, really all that matters is what's going on the seam. And these excursions are all frozen out. So not only do you have this sag, but you also have this idea of this kind of convergence like that. So yeah, go ahead.
We were talking about the sag and the seam threshold.
Yep.
I see at the very top, it's just quite a bit.
Yeah, so I'm just defining, I'm just fixing the ratio between the seam and the bulk errors to be what it would be, to be the ratio between the nominal seam threshold and bulk threshold. Okay, so for example, like we have the 10% and then the 1%. So I'm essentially saying I'm going to make the seam errors 10 times as big as the bulk errors, then scale those together up and down, and then see what comes out. Okay, just because otherwise it's too many dimensions to visualize. So yeah, I'm plotting in terms of bulk here. You're right, and that's. Yeah, I made that plot for certain reasons for the paper, but you could equally just plot this in terms of PS as well. Yeah. And when you look at it, we did numerics as well on this, just Monte Carlo using Oscar's wonderful pi matching, amazing tool. And you can see the exact same kind of behavior happens, right? So numerically, here we have the dotted is, again, just what happens with the bulk. Those are these curves. The dash is what happens when you have a noisy repetition code. Those are these dashed curves here. And again, we're plotting those in terms of bulk error. So there's like a factor of 14 actually difference between those. So we've kind of like essentially cranked up the errors on the seam until they're 14 times the bulk. And then we've scaled those down together to look at the threshold behavior. And then the solid lines are what happens when you have both together. So again, we see a slight sag, not too much, but a little bit of a sag. And then again, these curves kind of converge down to the seam only curves as you go a few times below threshold. What's also very instructive conceptually is to just plot out where the threshold lies in the space spanned by P bulk and P seam. So again, if there was no interaction between them at all, then you just would need to be below P seam and below P bulk. So anywhere to the left of this dashed line and below the dotted line would mean that you were below threshold for both failure modes independently, right? However, what we actually numerically simulate is this purple line instead. So points up here in this gray region, like right here, these are points that would have been below threshold if the errors were independent, but aren't actually below threshold because of the interaction between the seam and the bulk and the way these excursions contribute to ways to add logical failure. So things to note is that, yeah, we can actually exactly extract what this region is, but it's a relatively small region. So that's very promising for actually building something in a modular architecture. The other thing is this curve down here is actually the bound curve. So it's not tight even in the homogeneous case, but if we kind of put in the actual thresholds for bulk and seam, and then we kind of relax the counting of the number of ways to leave the seam, we actually get this kind of like light purple curve right there. So again, that's kind of like a fit to that parameter, but you can see that it's kind of qualitatively capturing the nature of the trade-off between bulk and seam errors and how that leads to threshold. So one takeaway to remember is that the logical failure really is kind of like a seam term and a bulk term need to be below both of those thresholds, right? Plus a small kind of like correction, which corresponds to this little gray corner up here, right? But what we found, and we were hoping to see, was that that's actually quite small, all right? And then the other thing to realize again is that once you're a few times below threshold, you not only you can actually even ignore the fact that there was that sag because you get this convergence to the seam only errors as well. Now, just to kind of like further illustrate the power of thinking about the error chains in this way, it's also possible to use this kind of formalism to qualitatively at least understand the effect of having multiple seams embedded in your system. So for example, instead of having two surface code patches with one seam in the middle, what happens if I have two seams, and let's say they're parallel for simplicity, and they're a certain distance apart. So we're going to call the distance between the seams h. All right, that's how far they are apart. what would we think should happen when those seams are closer together versus further apart? Well, if the bulk itself is below threshold, right, that means that we already know we have processes where we can fail by moving along a seam. We know we can like hop off and back on a seam, but now there's kind of an additional process that's available where you could run along one seam for a while, tunnel through the bulk, hop onto the other seam, and then keep going. And you could hop back and forth between the two seams as much as you like. However, the intuition that we've developed is that if the bulk is itself below threshold, the further apart these seams are, the harder it should be to actually tunnel across, because you have to append more and more edges through the bulk, each of which is costly in order to move between the seams. So we can actually numerically simulate and then also kind of like adapt the model that we've been talking about and the way we've been thinking about it to show that, yeah, if you have those two seams and they're very close, you get a certain amount of sag of the threshold that's caused by the fact that you have two. And then as you pull them further and further apart, right, they asymptotically approach just the sag that's the case caused by one seam alone. And once they're very far apart, there's very few hops in between them because it's very costly, right? And that's reflected in the math up here because our infinite sum now starts from h. You have to go at least h links, whereas for one seam, you only had to hop a couple of links. Now, again, kind of going back to our 3D decoding graph, this applies to a few different problems that would be potentially interesting that are coming up for stuff like Rydberg arrays, for example. If you wanted to link multiple modules, right, well, then you'd have multiple seams in kind of space and time, those 1+1 dimensional seams. And this kind of tells you something about the module size that you need in order to not see a whole bunch of extra sag from having your modules be too small. But again, you can also think about this in terms of transversal gates, right? So I think it's an interesting question. I've asked some quantum error correction people in the past before, if you do a transversal gate, how many rounds do you have to wait before you can do another transversal gate, right? How much error correction do you have to follow it up with? This is a little bit of an ambiguous question. So our results have actually indicated that if you're doing, really good memory error correction, and then you do a transversal gate and you keep doing that, and there was only one of these pink planes, we actually get the same level of robustness that we've talked about before. So we can do these transversal gates with like L-squared really noisy bell pairs. We're going to be super robust to that. So that's really cool. However, if I add a second one in here, that's just this problem I've outlined right here. And so this tells us as a function of like how far below threshold the bulk is, and then how far apart these actually are in time, how much extra performance hit I'm going to have in terms of my threshold, right? So it may be the case that with a certain level of bulk quality and seam errors, if I have them very far apart, I'll actually be able to function below threshold. But if I bring these two seams too close together, I'll no longer be below threshold. So it kind of illustrates all the trade-offs involved in that. And if you're actually substantially below threshold, you don't need to wait, L rounds or something in between these. You can actually stuff these much closer together. To Ben's point about the XDZX. Now, just to kind of illustrate a slightly more concrete application of this, well, you realize that the seam noise we've been talking about so far, we just kind of treat it very phenomenologically. We just said there's elevated noise due to the bell pairs. Well, there's also elevated noise due to the gates as well. Like there's overheads involved. You have to do a couple of C0 local gates. You have to do some readouts and local error, local rotations and stuff like that. And so we also just kind of took into account what how each of those would be expected to contribute to the total phenomenological error level, and just plotted out in terms of more experimentally important parameters like the bell pair infidelity itself, and then the local gate infidelity, so that experimentalists can get a sense of what this would be like. So you can see that this sag looks like it's sagging a little bit more, but that's kind of because there's also local gates contributing to the seam noise in this case. So instead of plotting it versus like just noise on the phenomenological seam and the bulk, now we're plotting in terms of the experimental parameters. And again, that sags more because as soon as you turn on the local gate errors, that itself also contributes to the infidelity of the teleporter gate in addition to the bell pair noise. And then just for comparison, this blue curve here is kind of a model to compare where if you were just doing teleported gates for every single C0 at the logical level, at the level of the code, and everything would be worse, right? You'd have a bell pair used for each one of those two, and so we just kind of a comparison curve to kind of understand the difference between having two code patches interfaced. You get the purple, whereas if you have really small modules and you can only do teleported gates between all the different modules to comprise the entire code, you end up with something which is much more constrained in terms of where the threshold lies. Other point is that this green star kind of represents current experiments, okay? Now, I'm not claiming that everything necessary for achieving this has been all pulled off at once, but it turns out the people in Lucan group over the last month or so have actually gotten their 2-qubit.
Attention occupants. This is a test of the fire alarm system. I repeat, this is a test only. Testing.
Do we have to leave or are we good? All right. I guess it worked. Yeah, the folks in the important things. Yeah, okay. The Lucan folks, they've recently got to 99.5% gates across about 20, 30 atoms, something like that. Paper will be coming out on that soon. And then the ion folks, they've worked the hardest on increasing the, having the best fidelities of remote entanglement distributions. So there's also papers where they've gotten down to something like 5%, right? And so again, there's a lot of work left to kind of like integrate this all into a whole system. But again, we think that the remote entanglement with atoms shouldn't be necessarily any harder than with ions. We think, I'll tell you in a second about integrating cavities even makes it potentially better. But you can see making it down past the purple line is a lot easier than making it down way past the blue line. So that's just something to keep in mind. Yeah. That would be for the Bell pair here. Exactly. For Rydbergs? Well, different groups have different numbers. Lucan group recently got to 0.5% CNOT infidelity. Yeah. I'll talk more about that in a second. Okay, so let's talk about Rydbergs. How does this all kind of apply to Rydbergs? This is our first kind of case study, taking this formalism and thinking about it, how it would work in a system. So if you're not familiar, there's been a number of papers recently. The experimentalists have done amazing work. They've been loading hundreds of atoms. Other groups have done this as well. I'm just talking about Lucans because it's kind of the world I live in. But yeah, they've been able to load them probabilistically, right? Grabbing them from the vacuum chamber essentially with these laser beams, rearranging them into these defect-free or nearly defect-free arrays and doing all kinds of very fun analog simulations and studying all kinds of fun physics. Safman and others have kind of estimated that with these current techniques using these same like acousto-optic deflectors and everything else there, we should be able to get up to something like 10 to the 4 atoms this way. So, quite sizable, maybe even able to support a couple of logical qubits at some point. Of course, there's limits like we saw before. So that's why this project is necessary. The other thing that's really nice when you want to think about building a module is that these atoms can be moved around. So Dolov and Lucan and everybody showed a year ago that you can take these laser beams and you can actually just move them and the atom will stay there. And what's nice is that the gate mechanism and also, the gate mechanism itself has nothing to do with motion. So the motion itself is totally decoupled from the way that you do gates. And if you're not familiar, the way that you do them is you have illogical information stored in, say, the spin state of the nucleus or the electron of the atom. You hit it with a laser to promote it to a Rydberg state, right? Which has a large dipole moment. And then you get a dipole-dipole interaction between nearby atoms that are, say, a few microns apart. So you can fairly selectively target which atoms you want to have an interaction on. But that interaction mechanism has nothing to do with the motional modes. So it's actually pretty distinct from the way that gates are done in ions, for example. So what's nice is that just separates out the gate mechanism from moving around. And this is great if you want to think about creating connectivity for different kinds of circuits and stuff like that. But hey, for getting the job done that we want to do, we're actually most excited about the motion because it allows you to create different kinds of zones, right? You can have atoms sitting somewhere, you can move them somewhere else and do a different kind of functionality on them. This is the area where we're reading them out. This is the area where we're doing the local gates. This is the area where we're doing, remote entanglement distribution. Like everything that you need, you can kind of partition the system into dedicated zones. And so we think that that's one of the most promising parts. So because it scales out quite a ways, because the motion and everything else is pretty decoupled from the system, and because crosstalk is really not too bad of an issue, you can have very precisely pointed small Gaussian beams which only address particular atoms. Our thought is that if you go back to our initial plot of the mean gate fidelity versus the module size, we probably have something that looks more like that before it falls off rather than something that goes like this. So the hope is that we can actually have quite a few atoms in there, all operating with this high quality and well controlled before of course, we do hit these kind of limits. So promising for making a module, in our opinion. So to kind of talk about some of the targets, I'm happy to chat about this more later. Single qubit rotations are great. Lucan group usually just got to 0.5% 2 qubit gate infidelity. A lot of modeling has suggested that we should be able to get to 3 nines, again, with kind of better laser systems, more power, certain technical reasons that upgrading that should get there. We think we can get to 10 to the 4 atoms per module, right? And kind of the result of this whole theory work and the way we thought about it, we now realize that if we have a few % infidelity bell pairs, the fidelity on those bell pairs itself is really not going to be limiting things either if we want to build a modular architecture this way. So the last question is, can we really generate those bell pairs fast enough between the modules to actually push the error correction forward and push logical gates forward between surface codes in different modules? Because if you can't even if you generate them with very low noise, if you can't generate them fast enough, well, the bell pair itself will die before you're able to actually push the thing forward into where your code cycle will be unacceptably slow. So what's the situation on that, right? But I would say, yeah, the result of all the theory we went through kind of pushes the problem from here. We got that finished. Now it's the question of the speed. Can we actually do this at a reasonable rate? So the general thing that we're thinking to do is actually augment the Rydberg arrays with optical cavities. So you just have the array, you also have a cavity. You can move atoms around, so you can put them in the cavity and not. You can kind of pipeline them so that they're all kind of streaming through the cavity, doing remote bell pair generation with another module, and then moved into place by your surface code patch. And then you're off to the races doing code cycles. We think that we can get really fast bell pair generation. I'm not going to skip a lot of the details here, but happy to chat more afterwards with you guys. We should be able to get something like a few microseconds per bell pair. And we think that in a kind of like future system we've worked out the parameters for, we could get code cycles of less than 100 microseconds. And the thing to note here is that that's way smaller than the actual coherence time of our atoms, which is something like 1 second when they sit in the ground state. So again, this is probably going to be the clock rate limit. But even with just one cavity, we think that we should be able to at least do code cycles well below the coherence time for logical qubits in different modules. And then, of course, if you can do it with one, then maybe you can parallelize, right? Why not have 10 cavities, 100, like engineer certain arrays of cavities and really get this off to the races. So this is an experimental group I collaborate with, actually. If you guys are in Boston, definitely stop by for a lab tour. They would be very happy to show you what they got. But we see this complicated looking thing like this. This actually kind of like goes into a vacuum chamber. And then there's mirrors on a ring here, which form cavity modes. And then there's lasers that are going to be shot from the top and bottom to actually do the trapping. This is going to be a system that has not only the Rydberg array in it and the ability to move those around, but also this cavity, which allows you to interface with the environment. And here's another pretty picture, kind of looking down this direction of this photo. You can see that that's one of the cavity mirrors there. So you can probe the cavity, you can have the atoms release photons into the cavity mode. And then also, there's going to be lasers from the top and bottom, which are going to be doing the trapping. So you get all the functionality of the Rydberg array as well. So yeah, things left to do on the experimental side. There's active work right now, kind of the results of all the things we've done last year, saying, yeah, we really want to integrate a cavity with the Rydberg array to demonstrate everything necessary to run these code cycles between modules. There's still a lot of optical engineering and stuff in order to actually get 1,000 to 10,000 with the 3 nines fidelity we're shooting for across the array, but that's an active development too. And then of course all these numbers that I went through, that's for one cavity. There's no real reason we shouldn't be able to do like parallelized nanophotonic cavities, moving atoms between them and stuff to really also speed up the clock rates if we want to have code cycles that are even faster. But yeah, we just wrapped up this theory paper. We have a Rydberg specific one coming out soon too. But I would be very interested to talk with you guys about not only applying these robustness ideas to other platforms, superconductors, ions, and stuff like that, but also what this could mean for other codes. So I'd like to thank my colleagues here. That's me with longer hair. This is my good postdoc, Josiah. Of course, the illustrious Nico was present as well for much of this work, and my great advisor, Laden. And then stay tuned for follow-up work, which will also include contributions from Dolov and from Misha. So thanks very much.
Are there any questions? On the numerical simulation, we have seen the whole in the service code. Do you literally just for applying errors with no one applying at a high rate and then in the code just providing those errors?
That's right. Yep. Now, Yep, that's correct. You just increase the level of errors on that. So I just took Oscar's pi matching. I said, okay, these edges need higher errors, and then just simulated it. Yeah.
I'm just thinking again, X is an X code, and the idea of what you do with this in one lower dimension. I mean, then I'm trying to figure out what the plot you would look for would be in that case, because you would just be using single pair uncorrected bell pairs to pick up the ends of these one-dimensional lines through the X code.
I see.
And then somehow it seemed, I'm trying to think of what would be the result that you would even want is just sort of just a sagging in the 2D in the XZX bulk threshold as a result of bringing it up and down. And the sag would just be proportional in some way to that error.
I think.
You wouldn't have these two.
Wait, sorry, you wouldn't have like this plot.
You couldn't make a plot like this because there's no threshold for the C. You don't have any encoding on the C.
Well,
it's just a bare bell.
Wait, are you thinking about analyzing the properties of like a single logical qubit in the XZX or like two linked XZX qubits?
XZX codes.
Yeah.
Where now if you're linking them
yeah.
at the ends of these 1D lines that you're decoding.
Well, okay, wait. So would you have something similar to, so you'd have a code patch, which is an XZX patch, right? Yeah. And you have another code patches here. So you can tell me maybe, so if you want to do lattice surgery between two different XZX patches, right? You'd link them up in the same way, right? So then I don't see why it would really be any different then, right? Because you'd still have elevated levels along the interface, right? And then you'd have excursions, right? Which could propagate all over the XZX code, as long as you're not in the super biased noise limit, right?
Yeah, I'm thinking, so this picture would apply.
Okay.
Except you do it in a rotated way.
Yeah.
You'd be decoding though your bulk codes along lines.
Like the diagonal lines you're saying from the paper? Yeah.
And so at the seam, your seam would just, be an unencoded bell pair connecting the end of one line and the end of another line. There would be no repetition code along the bound. There would now just be individual qubits where you not connect.
Well, are you saying that like when you did the seam in the XZX code, it wouldn't be along the direction, say, of like an XL failure, and so it would not necessarily contribute? Like what if you had perfect bulk in the XZX would be my question, and you had noise along the seam? Like what would it logically fail or not?
Yeah. I mean, it would fail, but I guess you're not. I hope I'm thinking of this the right way, but I feel like you're not using a repetition code along the seam now. You're just dependent on the individual failures of the individual bell pairs.
So, right, but if you had a whole bunch of errors along the seam, you'd still fail, right? And so you use something like a minimum weight perfect matching decoder along this, right? And so I still think it would be like a lower dimensional subspace decoding problem, right? Along the noise of the seam, even if you link those two up. Is that right?
Instead of having a 2D seam, series of 1D. I don't know.
I think so. Well, I think there's two different things we're talking about here. So one thing is like elevated noise along the actual like single interface we're talking about, right? And I think that would follow this paradigm. But then there's the other thing that like Ben was mentioning, which is that in the presence of noise bias, right? You have these kind of like parallel 1+1 dimensional planes, right? And that's more similar to what I was talking about here, right? Where, in the limit of infinite noise bias, right? You have planes which have no connection between them. You can't hop between either the 1D+1 dimensional planes. Yeah.
Sorry, this is the picture that I'm thinking of. And if you're decoding just within these planes, I mean, these are 1+1 planes. So I'm even sort of ignoring the time axis for a moment, you're linking up with the bell pair at the end of that one spatial dimension, one bell pair, physical bell pair across to the corresponding other 1D line on the other code.
Oh, so you're thinking like a diagonal string, which then like, and you kind of like have a lawnmower type pattern, or what are you?
No.
Because you're saying like the planes don't have to be connected now, right? In the infinite bias limit. Yeah. Let's talk about it more later. I think that as far as the interface between them goes, I think it would follow this paradigm still. But like, I think it's, yeah. Let's talk more about that later. Yeah. Any other questions? Yeah.
Thanks for the question, John. I think I just missed it what you said. We relax something on the stage which causes the sag and overall performance. What do we relax?
Wait, would that have been like here? Relaxing. So what we do is we just, well, yeah, I would say really what you want to think about is plotting out what the noise, what the logical failure rate is and its threshold in terms of the amount of actual error that's on the seam and on the bulk, right? And if I was saying relaxing, I think I'm basically saying like the fidelity requirements on the seam are relaxed compared to the bulk, right? So I don't need the seam noise to be at the same level of the bulk. I can have it way bigger, like 10% instead of 1%, right? And that's approximately true, except for this small correction up in the corner. Yeah. That's right. So it's just this small gray region, which is a correction to what would happen if you only thought about the seam alone as an error correcting code, and then the bulk as a separate error correcting code. So it just is very fortunate that, at least for the surface code, we know that the place that there's going to be the most noise is these interfaces, and it's also the place where we have this greater amount of robustness. So like a relaxation of the requirements necessary for fault tolerance. Yeah.